Good morning, physical science. I'm so excited. I've been waiting. I've been waiting to do this lecture because this is my favorite thing to lecture about. The name of this lecture, it's going to be lots of lectures on atomic structure, but today's title is The History of Atomic Structure. And teaching and lecturing on atomic structure, it makes me giddy. I love it. It's, I don't know, I like the history part of it. There's so many interesting, players in our current atomic theory, what it's based on, the people that contributed to this and what they had available to them to contribute to it. It's amazing. There's lots of figures, but I'm just going to talk about a few. This is my favorite thing to teach on. I'm super giddy. I need to keep things kind of neat. My feather duster, kind of, because if I'm going to lecture on my favorite thing, I want things to be nice and neat and tidy. And so I'm going to share my screen with you. I'm not that great at sharing my screen, I'm going to be honest with you. Sometimes I think I'm sharing one thing and I'm sharing something else, but nope, looks like I've got it. So first thing you need to understand, this is atomic structure. This particular video lecture is called The History of Atomic Structure. And this is really the basis for when you take chemistry from me, you're going to be glad I taught you this as ninth graders. But first, let's talk about the history. The history of atomic structure it's fascinating to me. These people, it's just cool. So let's talk about this. Now, remember, as I'm talking, if you want to stop, pause, write things down, I encourage you to do that. This is a little different than we've done in the past, where I usually give you a skeleton set of notes and you fill things in. You don't have a skeleton set of notes here. You have to write everything for yourself. I'll make it really obvious what I want you to emphasize by what I keep talking about, and I'll point to it. Hopefully you guys can see my little pointer here. But let's just go ahead and get into a very brief history. You have to understand that science, thoughts of science, theories in science, they all started out with philosophers. Democritus was not a scientist, he was a philosopher. But he was the first one to surmise that you couldn't continue to divide something indefinitely. Prior to him coming up with this idea, people thought if you had a hunk of matter and you cut it in half and threw half away and kept half, and then cut that in half, threw it away, kept half, you could keep doing that forever. It might get obviously way too small to be seen, but you would be able to keep doing it indefinitely. That's what they thought. And Democritus said, you know what? I think eventually you're going to get down to a particle that you can no longer divide and still have the same matter. Okay? I hate to bring cats into this, but it's kind of like this. If you have a truckload of cats, all right, and you take half the truckload and you let them go and you keep half, and then you take half of that half, let them go, funnel them towards my house. I'm kidding. And so now you have a fourth of your original one. And if you keep doing that, can you keep doing it forever? No, eventually you're going to get down to a single cat. If you cut that cat in half, you're not still going to have a cat. You might have a cat leg or half a cat or whatever. This is what Democritus was saying. Again, not a scientist. He was a philosopher, but he did give us atom, the term atom. He called it that. Then jump forward, like way forward, late 1700s. There's Democritus, by the way, fetching fellow. Late 1700s, scientists knew that elements combine in certain proportions based on mass. Okay, we had these things called alchemists, and they were kind of the predecessors to our modern day chemists, and they were trying, depending on where they were from, they were trying to do one of a couple things. The European alchemists were trying to take something cheap and readily available and turn it into gold. So they were doing lots of experiments to try and change matter that was cheap to have into something that was very expensive. Go Europe. The ones from Asia were trying to find the elixir of life. They were trying to find something that they could take that would make them live healthy and forever. Didn't really matter what their goal was. What they were doing was they were doing a lot of different research and experiments that gave us lots and lots of properties on the elements that they knew of at that time. So they didn't understand what an atom was. They didn't understand what made up matter, but they knew that if you combined these two substances, say hydrogen and oxygen, when they combined 2 to 1, hydrogen to oxygen 2 to 1, it would make water, H2O. So they knew this. 12 grams of carbon react with 32 grams of oxygen to form carbon dioxide. Now, here's what I want you to do, okay? I want you to go to your periodic table, and I want you to find carbon. Carbon is one of the main group nonmetals, upper right-hand corner, and I want you to look at that decimal number, okay? Look at the decimal number for carbon. If you round that to the nearest whole number, what do you get? You get the number 12. That's what they're coming from with this, okay? They didn't know all that stuff on the periodic table about carbon. They didn't know that, but they knew that 12 grams of carbon always reacted with 32 grams of oxygen. Now go to oxygen, just 2 over from carbon, okay? Look at its decimal number. Its decimal number rounded is what? It's not 32 though, is it? It's 16. But I want you to understand something. When they used oxygen, oxygen is found in nature as a little thing called a diatomic molecule. Forgive that horrible too, I'm writing with my mouse, but oxygen is found as O2. Each oxygen, if you look on your periodic table, I'm looking at mine right here, that decimal number rounds to 16, but when they're found as 2, 16 plus 16 is what? 32. Okay. Now, so this is what they knew by the 1700s. No real one person gets claim for this. 1803 comes along, all right? Let's talk about John Dalton. He's called the father of atomic theory. He, based on research and experiments that had been done by the alchemist, experiments that had been done by him, he published this atomic theory. And there's several parts to it, but we can kind of boil it down into this little nutshell that all matter is made of atoms, small particles that cannot be created, divided, or destroyed. That's the first thing. Then he said, atoms of the same element are alike. If I have an atom of carbon in this hand, it's going to look a certain way. If I have an atom of carbon in this hand, it's going to be exactly the same. All atoms of carbon are the same. Later on, they don't know this yet, but later on they find out that it's carbon because it has 6 protons. But again, that's down the road a ways. Then he also said atoms join together to form new substances. Carbon and oxygen make carbon dioxide when it combines 1 carbon to 2 oxygen. If it combines 1 carbon to 1 oxygen, it's carbon monoxide. So those were the main parts of his atomic theory. All matter is made up of atoms. Atoms of the same element are exactly alike, and atoms join with other atoms to form new substances. This was his theory. There's lots he didn't know, but all other people's theories kind of based off of this. They were actually trying to prove this guy, John Dalton, right or wrong when we came upon other discoveries. So there's John Dalton, fetching fellow. 1897, the first discovery that made us understand that atoms actually are divisible, all right? If we were to draw the atomic theory or the atomic structure, what we thought it was now, according to John Dalton, we would just have one hard thing called an atom that could not be divided any further. That's what we would have. This would be the current atomic structure, the current theory of what an atom looks like. Okay, then old J.J. Thomson comes along, okay? And there's no P in his name. It's not a typo. He didn't have a P in his name. J.J. Thomson discovers the electron using a cathode ray tube. Now we know there are smaller particles inside of an atom. I will post a video link on our document that talks about this cathode ray tube. But basically, he discovered that there was a negative aspect to it. And he was using metals to generate a stream of electrons. And then he was able to bend that stream of electrons one way or the other with magnets and with positively charged plates. But again, there's I will put a link on our website or on the document that shows you the cathode ray tube. I really encourage you to watch that. It's easier for me to explain this if I have a whiteboard. So I'm going to have to rely on some other people that have explained it in the past. Probably the Harry Armbag. He thought that the atom looked like this. There's a negative particle. He did call it the electron. Amazingly enough, he actually figured the mass of that electron, and he was really, really close to what it really is. So what he surmised was, here's our atom. So instead of just being this round blob that can't be divided, like they thought up until this time, and what Dalton thought, he said that here's the atom, this whole blue circle is the atom. This blue is a sea of positiveness, all right? He knew that there had to be a positive aspect because matter itself did not have a charge. So the atoms that make up matter could not have a charge. So if there's a negative aspect that he discovered with his cathode ray tube, there had to be a positive aspect to neutralize that or to balance it out. So he thought we had this big blob of positiveness with these little negative electrons stuck in there. It was kind of like if this is a cookie, the blue is a cookie, these are the chocolate chips. It's called the plum pudding model. Plum pudding model. I want you to write that down. We don't really understand plum pudding. It's more of an English dessert, but it's just a pudding with plum stuck in it. We're going to go cookie with chocolate chips. And again, I'm going to post this video on the document that you can watch. Or, you know what? I don't see why we can't watch it now. Maybe. Nope, don't know how. Okay. Let's go on to, there's JJ. I personally like that his glasses just sit on top of his nose and he doesn't have anything that goes over the ear. I think it makes him cool. 1909 to 1911. So now everybody is embracing the plum pudding model of the atom, J.J. Thomson's, that there is a negative aspect to it. Along comes Ernest Rutherford. Ernest Rutherford was really kind of trying to prove that, let me back this up. He was trying to prove that Thomson's model was right. And he used the gold foil experiment, okay? He discovered that the electrons are not stuck in the middle like this, that there's a very hard, dense center, called it the nucleus, and that the electrons are outside of the nucleus. He did this using the gold foil experiment. So now, and again, I will post this, the gold foil experiment on our page. You can have lots of stuff you need to watch. But so he discovered the nucleus, found out that the electrons were found flying around out in this yellow part, and that this very hard, dense, positively charged center of the atom that he called the nucleus. Everything else was just kind of called the electron cloud. It's just where everything else was found. Just in a nutshell, this is what he was doing. He had a very thin sheet of gold foil, and he was shooting alpha particles at this gold foil. Alpha particles are the result of radioactive decay. When something naturally decays, we knew about this. Madame Curie had already figured this out for us. Some of the things that are ejected from a radioactive atom are alpha particles, which are just 2 protons and 2 neutrons. It's basically the nucleus of a helium atom. Anyway, you have something that's radioactive, you stick it in a lead box, you make one tiny little hole, and those alpha particles are going to come out that hole. It's the only way they can come out. They're coming out of that nucleus at high energy. They're going to shoot through that hole, and he was shooting them through gold foil. Most of them passed right through it. But every once in a while, one would get diverted. He had a screen behind this gold foil sheet that when something struck it, you could see where it struck it. It would like illuminate. And he would notice that they weren't all passing straight through like they thought they would. Some of them were diverted one side or the other. In fact, some came bouncing straight back, and that completely floored them. They could not, they said having one of those alpha particles come straight back would be like shooting a cannonball through a piece of tissue paper and having the tissue paper bounce it back. That's how astounded they were. And they said, there's no way that the atom can look like this, that there has to be something very hard and dense in the center that those alpha particles were hitting that caused it to bounce back. So Ernest Rutherford discovered the nucleus. So now our atomic theory, our atomic model looks like this, where we have the nucleus. They didn't know what was giving it the positive charge, but they knew it was very dense and positively charged. And then around the outside are all the electrons. Next. I know this is a lot to take, but here I'm putting my electrons in there. Ding, ding, ding. There's Rutherford. It's kind of weird. He looks a lot like my great-grandpa Marble. I have a picture of my great-grandpa Marble. He looks like that guy. Could be the mustache. Anyway, so we've gone from Democritus saying matter cannot be divided indefinitely, philosopher, okay? Then we had Dalton that came up with his theory that matter is made up of small things called atoms, that the atoms of every element are exactly alike, and that atoms combine with other atoms to form new materials. Then Thomson comes along and says, holy cow, the atom can be divided further. It's got this negative thing that I bent with positive and negative plates in the cathode ray tube, but they're just kind of stuck in the middle of this cookie dough type stuff. And then Rutherford comes along and says, man, there's something super dense and positively charged in the middle of that sucker that's causing these alpha particles to bounce back. So we've gone from just a hard dot to the plum pudding to this, nucleus, electrons on the outside. Here comes Bohr, Niels Bohr. Niels Bohr observed the way that atoms react to light and surmised that electrons travel in certain paths around the nucleus depending on how much energy they have. I'm going to nutshell this for you, okay? He was messing around with hydrogen, and he was taking electricity and passing it through a sample of hydrogen in a tube. And he noticed that this hydrogen, when electricity was passed through it, would emit light. So he took that light and he bent it with a prism, and he found out that it emitted, I can't remember, 5 or 6 different types of light. You know, like when you see a rainbow, it's because white light's passing through a raindrop, and the raindrop separates the white light according to its frequency or wavelength, and then you can see red, orange, yellow, green, blue, violet in that order. He saw 5 or 6 colors that hydrogen was emitting, and he realized hydrogen only has 1 electron. It's not like there's 5 different electrons that are producing these light. And this is, I mean, we're getting into, this is chemistry type stuff. But basically he surmised that the 5 or 6 different colors, and I should have known how many there were, but it's right around there, weren't from several electrons emitting this light as they fall from one energy, as they emit this light, that they're falling from different energy levels. So all you really need to know about old Niels Bohr is that we took the electrons, and instead of just having them flying around out there like Rutherford said, they're actually in levels according to how much energy they have. And there's Niels. He had a son that did a lot of work too. I will draw all of the models for you in a later lecture. All right. Then 27, Schrodinger and Heisenberg. They further explained that electrons do not travel in certain paths, but their location can only be predicted as to where they are likely to be. So it's kind of like we were doing this. We were getting closer and closer and closer to where these different parts of an atom are found. All right. Went from an atom that was just one thing to it had a negative aspect, to it had a positive nucleus, that the electrons are outside the nucleus. And then we said, well, man, they're actually in different energy levels. Now we're going to be able to find the exact location of an electron. Then Schrodinger and Heisenberg came along and they said, you can't. They're moving so stinking fast that you can't really tell exactly where they are. But we can have areas of high probability. They're called orbitals. If we were in the classroom, I would draw a really cool drawing showing you the different orbitals. And then I'd show you some really cool connections with the periodic table. Until I can figure out how to do this remotely, you're just going to have to, this is a little bit substandard, I realize, but I promise when you get into my chemistry class, I will explain those to you. So here's Schrodinger. They work together a little bit. They're kind of lumped together because they kind of did some same studies, but they didn't really work together all the time. They just, anyway, so there's old Schrodinger, Schrodinger's cat, you know, look up Schrodinger's cat. It's really interesting. Bradley, I'm sure you probably already have. And then here's Heisenberg. No, it's not Heisenberg. That's from a show that you guys shouldn't watch. That's the Heisenberg from Breaking Bad. This is the real Heisenberg, okay? And I think he looks like Henry Krantz. Anyways, so now that you have the basic structure of an atom, let's look at each part a little bit closer. That's what we're going to do in the next one. The next video that I'm going to post tomorrow is going to be how our model of the atom has progressed over the years. And I'm going to play a song for you guys that talks about all of these people. I hope that I can get to it. If you guys were in class, we would listen to this song every day until you all got this history stuff down. But we're not in the classroom, so I'm going to play it for you. It's one of my favorite songs. I can't believe it didn't make the top 20. It really should have. Hurry up. All right. Oops, blank page. We don't want that. No idea what's coming up. Be great if it was a song. I don't think this is it. Let's get rid of this. Go away. All right, these are the different videos. All right, this is my song. Pretty excited about this. I might post a link to this song every day this week. Listen, it talks about everything that those guys do. Turn it up.
Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg, and many, many more. Use their brains to venture in the realm of inner space and found the world on the end was a weird and wondrous place. Dalton did experiments, said I think it's clear. Atoms are tiny indestructible spheres. Thomson worked with cathode rays, said I disagree. A plum-pudding model makes money more sense to me. A new chapter in atomic theory started to unfold as Rutherford played around with atoms made of gold. When a few of his alpha particles came bouncing back, he hypothesized the nucleus had knocked him off the track. Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg, and many, many more. Use their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place.
I think that's Tamara playing the bass. Probably not. There's more.
Bohr saw spectral lines for hydrogen. Instead, it seems to me electrons move in orbits with specific energies. Heisenberg said, forget it, there's no way to know the orbit or a path where the electrons could go. Schrodinger used lots and lots of
Fancy mathematics.
made a model of the atom based on quantum mechanics. It has orbitals, and those are based on probability. The atom is a fuzzy blob of pure uncertainty. Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg, and many, many more. Use their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Dalton, Thomson, Rutherford and Bohr, Schrodinger, Heisenberg, many, many.
Fading it off. So, I really seriously want you guys to click on all the little videos that I'm putting on the page today. The first quiz, you need to watch this video if you want to understand. Dogs are barking. If you want to do well on the quiz. So watch all the things that I post, and I'll see you guys on the other side.